So let's look at some problems for rate law. Specifically, I'm going to be looking at question number 4 in the practice problems that I've assigned you. And I think this is a good question because it covers all of the different types of ways you might be tested on this type of question. So in a question like this, you're given the reaction up at the top, and you're given 4 different trials, each giving you the initial concentration of each of those reactants, as well as the rate of production. So there's 4 different trials here. And based off of this information, we are asked to find the order of reaction with respect to each of the reactants. So essentially what we are doing is finding how the reactant affects the rate of production of the products. In order for us to do that, we have to first write a rate law expression. So what we know is that R is equal to K, which is a constant. We'll talk about that in the next section, times the concentration of A, times the concentration of B, times the concentration of C. But something that we need to note is that the way that concentration of A affects the rate might be different than the way that the concentration of B affects the rate. So in order for us to figure out how these are different, we have to find the value of the exponent that comes with this. So I'm going to right now write this as a letter. So A to the power of M, B is going to get to the power of N, C is going to get to the power of P. So let's find out the value of M. Now, when I'm looking for M, I have to choose 2 of the trials that I'm given. And there's a set of criteria that I have to meet when I'm choosing these 2 trials. In both of those trials, I have to make sure that the concentration of the other reactants have to stay consistent between them. So let's choose trial 1 and 3. If I'm choosing trial 1 and 3, my other reactants, so that's B and C, have to be consistent between them. The concentration has to stay the same. So let's look at C. So between 1 and 3, the concentration of C is 0.1, 0.1. So that does stay the same. If I'm looking at the concentration of B, it's 0.1 for trial 1 and then 0.3 for trial 3. So that doesn't really work. So let's try if we choose, I'm just going to change the color of my pen. Let's try and choose trial 1 and trial 2. So in trial 1 and 2, let's check for the concentration of B if that stays consistent. So this is 0.1, this is 0.1. It does stay consistent. The concentration of C, 0.1, 0.1. Okay, so my trials that I'm choosing are trials 1 and 2. Okay, so I've done that. Now what I'm going to do is look at how the concentration of A is changing between those trials. So the factor by which the concentration of A changes. So let's write that in. So factor I'm going to write it all out in a lot of detail for this first example, and then the other 2 I'm going to move kind of quickly. So in order for me to find out the factor by which concentration of A changes, I have to divide these 2 values. So I'm going to choose trial 2 to become the numerator. So I'm going to write 0.20 divided by 0.10, which gives me the value 2. Okay. Now, I'm also going to look at how the rate changes between those 2 trials. So, factor by which, I'm just going to write R, changes. And I'm going to do the exact same thing. And because I chose trial 2 to be my numerator here, I'm going to choose the rate of trial 2 to be the numerator in what I'm doing next as well. So 1.2 times 10 to the power of negative 3 divided by 3.0 times 10 to the negative 4 is equal to, and when I put those two values into my calculator, I get 4. So now what we've done is we've found out how the concentration of A changed between trial 1 and 2, and how the rate changed between 1 and 2. Now, because the concentration of B is consistent and the concentration of C is consistent, we know that whatever changes occurred in the rate had to be due to the concentration change of A, which is why this allows us to find the accurate value for M. Anyways, so in order for us to find M, we have to put these two values, or write the relationship between these two values. And that is this: 2 to the power of M is equal to 4. And 2 to the power of M is equal to 4. If we know this, we know that only one value can help satisfy M, and that is 2, right? 2 to the power of 2 is equal to 4. So that tells me that M is equal to 2. Okay, that was how we figured out M. Let's see if we can solve for N. I'm going to change colors here. If you want to pause and maybe try this yourself and then come back and check to see if your answer is right, that works. Maybe I will choose a green. Oh, no, I didn't choose a green. Choose a green. Okay. So let's do the exact same thing. N is an exponent of the reactant B, so I'm looking for two trials where A stays consistent and C stays consistent. And these two trials are 1 and 3. So let's check again. Concentration of A in 1 is 0.1. The concentration of A in 3 is 0.1. So that stays consistent. Same thing for concentration of C. So let's write that out. Trials 1, 3. Now I'm going to do the exact same thing. See how the factor, or see if I can find the factor by which the concentration of B changes. Now I'm not going to write all of that out. I'm just going to designate it by writing concentration of B. Put a little arrow to see if we can find that out. So I'm going to choose one of either trial 1 or 3 to be the numerator. I'm going to choose trial 3. And it doesn't matter what you choose as long as you're consistent between this calculation as well as this calculation. So 0.3 divided by 0.1, that is 3. Let's do the same for rate. So in trial 3 and trial 1, I'm going to choose 1 to be my numerator, 1 to be my denominator. And because I chose trial 3 to be the numerator, going to do the same thing here. Not that it matters because it is the exact same value. But in case it was different, that would play a huge role in the answer that you get. Oops. 10 to the power of negative 4. So if I divide these two values, I get 1. All right, let's write the relationship between these two. 3 to the power of n is equal to 1. And this might happen often. And this relationship, you should know that any value to the power of 0 is always equal to 1. That means that n is equal to 1. Sorry, n is equal to 0. So just keep that in mind. If you didn't know that yet, please make sure that you know, because that might come up in rate laws. All right, let's change our colors. Ooh. Pen color, let's do magenta for P. Same thing, gonna choose two trials where concentration of A is consistent, concentration of B is consistent, and those two trials are 2 and 4, it looks like. So A stays at 0.2, B stays at 0.1. Let's find, so I'm going to write trials 2, 4. If I'm looking at how concentration of C, the factor by which the concentration of C changes, I will do 0.2 divided by 0.1. I'm going to choose for trial 4 to be the numerator. I get the factor 2. If I'm looking for how rate changes, I'm going to again choose for trial 4 to be the numerator, just because I did that earlier. 2.4 times 10 to the negative 3 divided by 1.2 times 10 to the negative 3, which gives me a value of 2. All right, let's put these two together. 2 to the power of p is equal to 2. So what is the value of p? P is equal to 1. All right, so I figured out the order of reaction for each different reactant. So B is asking you, write an expression for the rate equation. So all I have to do is take the information that I learned previously and put it all together. So I know R is equal to K times concentration of A times concentration of B times concentration of C. So the exponent of A, M, was 2. A to the power of 2. B, 3 to the power of n is equal to 1. So anything to the power of 0 gives you 1. So B is to the exponent of 0. And P has the exponent of 1. Now, because B has the exponent of 0, I can also rewrite this expression as R is equal to K concentration of A squared concentration of C. Just because I know now that changing the concentration of B does not affect the rate of reaction. All right, let's move on to calculating the value of the rate constant. So I mentioned this earlier, but rate constant refers to the value K in our rate law equation. A squared C. And we have to find this value. In order for us to do that, I'm going to choose any one trial. I'm going to choose to use 1, but you can try this calculation with 2, trial 3, or trial 4, and you should still get the exact same answer. So the rate of, so I'm going to sub in all of the values that I'm given in this trial. So I'll have K left over, and I'm going to solve for it. So 3.0 times 10 to the negative 4. And units in this question are very important because we are also finding the units of K. So 3 times 10 to the negative 4, the unit of rate of production is big M over S, or another way of writing that is moles per liter times second is equal to K. Then we've got concentration of A, which is 0.1. Now, concentration of A is squared. So everything inside of this bracket, everything that is concentration of A gets squared. So it's 0.1 squared. The unit, which is moles per liter, it's moles squared divided by liter squared. Okay, that's because everything that's the concentration of A gets squared. So it was at 0.1 moles per liter, but because we're squaring it, order of operation 0.1 squared, mole squared divided by liter squared, times 0.1 moles per liter. Now, since these are multiplied, I can simplify this by writing, so 3.0 times 10 to the negative 4 moles per liter times second is equal to K. Now, if you are multiplying this, and you've got the same exponents, the same value, and the exponents are different, you can add those up. So instead of it being 0.1 squared times 0.1, we can write that as 0.1 cubed. Mole squared times mole, we can write that as mole cubed. Divided by, again, liter squared times liter, liter cubed. And when we take this over to our other side, I'm going to try and write small. 3.0 times 10 to the negative 4 moles per liter times second. I hope that's clear. Okay, liter times second times, because of order of operations, I want K to be the only thing left over on this side of my equal sign. So L cubed goes on top. And then I've got 0.1 cubed mole cubed. All right, let's cancel out some units where we can. So if I've got mole cubed here and mole here, this gets canceled out and this becomes a 2. If I've got liters here and a liter cubed here, this becomes a 2. So my units for this, up at the numerator, the only thing I have left over is L squared divided by mole squared times second. And when I plug these values into my calculator, 3.0 times 10 to the negative 4 divided by 0.1 cubed, I should get the value 0.3. And that is my value of K. Now, something that I want you to try, maybe see if you can do this with trial 2 or trial 3 or trial 4, just to make sure that you get the same answer. You will. That's why this is called a rate constant, because it is constant between the trials. All right, let's do question D. So in this question, we're asked to find the value of R, right? So it says calculate the production of X when the concentration of A, B, and C are all 0.4 moles per liter. I'm going to first write out my rate law equation. I'm going to solve for R. I'm going to use the constant that I just learned from my previous question. Let's use gray. So it was 0.3 liter squared divided by mole squared times second times concentration of A squared. So again, remember what we did earlier, right? 0.4 squared times mole squared divided by liter squared times 0.4 moles per liter. Actually, I think we can just cancel out units right here. So I've got mole squared here, mole squared here. I can just cross those two out because they two cancel. L squared, L squared. All right, and that is it for the units that I have. So the units that I have left over, moles per liter times second, that makes sense because that is the unit for rate. When I put these values into my calculator, I should get 1.9 times 10 to the power of negative 2 moles per liter times second. Okay, that is how you do the 4 main things that you might be tested with regards to rate law. Be also comfortable in writing the expression itself and finding out those exponents because that plays a huge part. All right.